So good. So shall I share my screen? Presumably yes. Huh? So okay, let me just do it. Oh, sorry, this one.
All right, Miroslav, do you want to do the formal introduction?
Yeah,
as
sure.
you always do? All right, great.
Okay, so welcome back, everyone. Today we are happy to have Joerg Teschner from Hamburg, who's going to give us the second part of his talk on geometric characterization of topological string partition functions. And yeah, thank you for joining us.
All right, yeah, thanks a lot for, well, giving me even a second chance to say something here on our work with Joanna and Pietro and Ellie. Good. Of course, it's a bit of a challenge now to find a good point of re-entry into the subject, but let me maybe just repeat the slide for, well, posing the question and motivations. So good. I don't want to motivate study of topological strings in this round, but that's what we want to do. And good, we have via, well, just string theory, worldsheet description, or Gromov-Witten theory in math, definition of topological string as a formal series in some powers of lambda, the topological string coupling. And yeah, the goal is to discuss, come up with a non-perturbative definition. So this is sort of part one of the challenge or problem, to find an actual function having such an asymptotic expansion. But then furthermore, and that is in some sense perhaps the main concern for us, to find out if there is a nice like global structure behind that, which would tell us, well, if we have determined it somewhere in either Kähler or complex structure moduli space, how would we continue it all over that space? So what is the rules? What are the rules determining such a continuation? So the dream, which in our example we're going to find fulfilled, is that yeah, we can basically identify this guy here using, and this is what we shall explain a little bit, some line bundle on some natural line bundle on these moduli spaces here. Okay, there's a lot of fine print, and we shall remind or explain a little more about this. There's a class of, well, there's a playground, there's a class of examples where we can do something fairly concretely and with some control. These are these local Calabi-Yaus we call of a class sigma. So there's an underlying Riemann surface we call C. And then we're defining, with the help of a quadratic differential defined on C, a curve in the cotangent bundle of that Riemann surface. This is, well, has many names depending on the context you're interested in. Spectral curve, Seiberg-Witten curve, and so on. So this is related to geometric engineering of class S supersymmetric field theories. That is what makes Seiberg-Witten context. But it also has relation to some integrable model where it is the Hitchin moduli space, and then it would be the spectral curve thereof. And yeah, the main players here, the main geometric objects are, well, moduli space B for base manifold ultimately, which is the moduli space of complex structures of this class of Calabi-Yaus, which would be specified by specifying the underlying Riemann surface we work on and the quadratic differential we put on it. Good, there's special geometry. I don't want to remind this, but I want to remind that it is important for us that we have a kind of canonical enhancement of this, which comes with the geometric structures of B, the base. So we can make it a torus fibration, where over each point of the base we put a torus fiber, which is yeah, concretely determined by the geometric structures on the base. Okay, so M and B are our key players. So basically, it is all about the geometry of basically ultimately M, but this in turn well, appears to be mostly determined by structures or data associated to the base manifold B. All right, so I shall skip most of the first parts, jump to some little summary I've prepared at the end, maybe jumping back to some reminders here from the first part on the way. But I want to, I mean, the idea is here, and you can, push me or modify sort of the talk perhaps as to some extent. The idea is maybe that after some summary of the first part, some reminder with some added comments, I want to invite to discussions of some points which may be interesting for future research where parts are known, but well, in total, I should say that I feel this, what we're doing here is the tip of an iceberg, and I think there's a lot that probably can be done along these lines. All right, so here I want to go through this slide, serving the task of a summary of the first part in a brief and schematic way. We had quickly recalled M, the moduli space, which is going to be our main player, a canonical torus fibration over the space B of complex structures on our local Calabi-Yau's. And in this context, thanks to some theorem of Donaghy, Diaconescu, and Pantev, we can identify this torus fibration, in fact, with the intermediate Jacobian fibration, which is, of course, an important canonical object in this context of Calabi-Yau's. Yeah, then a first step was, well, we were describing our Calabi-Yau through sort of the curve of its singularities, which was this curve in the cotangent bundle of the Riemann surface C. And the first step is that we need to somehow deform this. This is giving sort of the classical structure, the classical story. And the first step is to deform the curve into what was called a quantum curve. Let me maybe flash how the quantum curve looked like in our cases. These were differential operators like that we simply obtained basically by the replacement. So y and x turn out to be canonical conjugate coordinates. So we quantize y by replacing it by the differential operator, leading us to such differential operators of the second order, also related to what is known as operas. Okay, so that is what we call a quantum curve. There was some, well, modification, which I argued is pretty canonical, that we have to add basically in order to describe in these terms how to go from B, the base manifold, which is parametrizing here the Q's essentially, to some objects which are defined actually on M, the torus fibration. This comes by allowing certain types of extra singularities, which, however, in the end of the day are pretty canonically determined by what we started from, or more precisely by sigma, which is determined by Q, and then a divisor, which is by Abel map related to a point on these torus fibers, and the divisor basically determines where the singularities sit, and then the rest, residue, and so on is just automatic. Okay, so this was
Joerg, I'm sorry.
Yeah. No, fine. Please
can you just remind us briefly
yeah.
You somehow said this, but I still don't understand. In which sense this was canonical?
Well, okay.
I'm happy to see that you have parameters h bar and so forth entering there. So in which sense was this canonical?
Yeah, okay. So this, of course, would a good explanation would really take a bit more time. I was here.
No, don't have to give us a good explanation. Just
I was trying to
really
give some indications, right? So what is relatively classical is that, okay, when we have these, well, the curve, then we can consider over it its Jacobian, which is then putting the torus fiber over each point on the base. Points on the Jacobian in turn are equivalent to divisors on our curve sigma. So what I was saying is that there is a essentially unique way of modifying here the quantum curve by just using the same divisor, which is describing the points in the torus fiber, This is then here describing the locus of singularities of these extra singularities. So these extra singularities are entirely determined basically by the position of the extra singularity, because all the rest is basically canonical. Here's one term of order h squared, which is just given by, again, the position. And there's an extra parameter, which in turn is determined by the equation of the curve itself, right? So everything here is determined by the divisor and nothing else.
Yeah, so why did we get an extra point? So in general, you said...
Okay, so what I'm simply saying here is that the quantum curve only knows about points on the base. And there is a very natural way to create a modification of the quantum curve, which is parametrized by the points in the torus fibration, in the full space and the total space. So the total space is the parameter space for these modified quantum curves, whereas if I just drop these quantum corrections, which is something I can do, which is basically just the submanifold of operas in the total space. So there's a Lagrangian submanifold in our total space where all this is dropped, but this is sort of a very natural deformation, which is determined just by a point in the torus fiber, point 1, and second, furthermore, and this is what I would call the real explanation, it is basically the canonical H-bar deformation of the integrable structure, right? The integrable structure on the torus fibration is the trivial one, and you can relate it to Hitchin if you like. Here is an integrable structure with these quantum curves related to the isomonodromic deformations of these guys. So the deformations of these differential operators preserving monodromy. What you can show, but this is non-trivial, is that when you turn off H-bar, so if you compute the classical limit of isomonodromic deformation equations, which is a little bit tricky, but can be done and it's known, what you recover is the flows, the linear flows on the torus fibers. So it is really basically in this context, the most natural geometric way of deforming the quantum curve, preserving the integrable structure, if you like. So it's a kind of integrable structure preserving deformation.
And in terms of relation to Liouville, which you do have here, the differential equation you end up with are exactly the same ones that are satisfied by degenerate fields at this point, is inserted at point U. Is that correct?
This is correct. Of course, this equation is related to, the classical degenerate fields or classical limit of degenerate fields. And what you may furthermore notice, if you have the background of Liouville theory in mind, then this would be sort of the differential equation satisfied by so-called weak degenerate fields, those whose parameter is vanishing with H bar. But then you could, in addition, consider strong degenerate fields, which would appear exactly as these extra singularities, right? The strong degenerate field, the other guys which have a parameter which is getting strong in the classical limit, they would modify here the singularity structure of Q, and these are exactly the so-called apparent singularities. So both sort of are present here, but they play different roles in this particular context.
I see. Okay. Thank you.
Okay, good. So this was point number 1. We go from curve to quantum curve, and basically, the goal is somehow to have canonical or very natural definitions of partition functions associated to the quantum curves and the moduli spaces they live on. Good. Then, the next step was to argue that when we take into account H bar, then it's natural to form what you might call a holomorphic variant of the twistor space, where you add the C star factor for which then the parameter H bar, the quantum parameter, would form a coordinate. That is, as usual, sort of when you have, for example, hyperkähler structure, a useful thing to do. What the space will parameterize are monodromy data for quantum curves. I mean, after all, okay, the H bar is let me stay here for a moment. The h bar is one of the parameters in the quantum curve plus all the rest. So all the rest were here all the other parameters that you see here. These are what you could consider coordinates for the moduli space M. Sorry if this is annoying to jump back and forth, but maybe at some points a reminder may be helpful. Good. So now really the main point is sort of, it's all about coordinates. So it's all about, say, covering this space here with a good atlas, a kind of preferred or even canonical atlas, where on the one hand we have to specify how charts are defined. So here they're associated basically to patches in the base manifold by plotting the Stokes graphs that they define. So here a quick reminder as well. We have a quadratic differential, which is basically the leading part for h bar to 0 of our quantum curve. We form, well, the square root thereof, that is the canonical differential on our curve. And then we're just plotting the lines, say, of imaginary part equal to constant, where we may rotate the phase a little bit by the phase of the quantum parameter. Well, sorry, I didn't correct this. So lambda is h bar. So just keep in mind, lambda topological string coupling is essentially h bar. And then we have the basically canonical coordinate that the quadratic differential defines locally on the spectral curve, on the curve sigma. So we say, we have a collection of lines here which emanate from branch points, fall into punctures generically. So here are some examples plotted for a 3-punctured sphere with the punctures here and there in the corners, and then they run off maybe to infinity. But there, it may also happen that these Stokes lines close up. That is particularly interesting case and form such a closed graphs, which are also called, to remind the terminology, Fenchel-Nielsen type Stokes graph, whereas such generic types would be called Fock-Gontroff type Stokes graph. The reason being that, well, in this case, we can define a triangulation of the surface from the Stokes graph, and there are associated coordinates to it in the end of the day of Fock-Gontroff type, whereas here they are of a closely related but slightly different type, which we call Fenchel-Nielsen type coordinates, indicating some relation of the classical Fenchel-Nielsen coordinates for Teichmüller spaces. So these are the Stokes graph, and when you vary the quadratic differential, the shape varies. It may undergo jumps at particular loci in the base manifold B, and may turn, for example, from such a type to such a type. Of course, this is not immediate, it goes through some steps. And yeah, the point is that then the charts are defined by a type of Stokes graph. Like this one would be one, say, for example, on the 3-punctured sphere, we have here these 4 types of Stokes graph of Fock-Gontroff type. For each, we have an associated chart and we have associated coordinates. We want them to be Dabou coordinates. I mean, we only consider Dabou coordinates here. So this is the kind of thing we are dealing with. All right, so yeah, we want to make it a canonical atlas. We have defined charts, and then the next step is to define the actual coordinates. And here again, what we're using is this context of exact WKB. Namely, it turns out that we can we can define solutions to the equation defined by the quantum curve by Borel summation in each of the regions defined by our Stokes graph, and we can use this to define the so-called Worosz symbols. And from the Worosz symbols, we can define, I mean, they are by their definition already functions on our moduli space. And if we're clever enough, we can use the combinatorics of these graphs in order to define coordinate systems. For each type of these graphs, we're getting a coordinate system on the underlying moduli space on our moduli space M. So this is the coordinates. Yeah, and then where our partition functions or tau functions come from, this is basically a canonical line bundle over our space Z, this so-called twistor space. And here, a very quick indication how that works. This is not yet to be confused with a topological string partition function. How this is extracted from the tau functions will be reminded in a moment. But I want to mention, at least briefly, that what the Fenchel-Nielsen type networks, I mean, just have a look here again. So these are these guys. So here we see two punctures, and they are enclosed by this network. So in particular, well, we can draw a curve here separating them from the rest of the surface to which it is glued. So two punctures surrounded by a curve, which is defined by this type of network. So these Fenchel-Nielsen type networks naturally define Pans decompositions. So for that case, which is a family of cases that just happens inside of our moduli space, what we can do is to use the factorization of the Riemann surface as defined by this graph into pieces, say a subsurface C2, subsurface C1, and then glued along an annulus that connects the two. And that leads to a factorization of the corresponding tau function, which is the section of the line bundle we're associating here to our moduli space Z. And yeah, here is, this is what I wanted to briefly mention at this point. Here is really the explicit relation to free fermions, because it's simply an overlap in free fermion theory between a state, which by some pretty canonical and well-known conformal field theory construction we're associating to the surface here. And we can associate another free fermion state to another surface out here. And then we're just taking the overlap, and this defines the tau function, and mathematically it's a relatively classical result, or something which is probably pretty well known, that such overlaps of free fermionic states have a Fredholm determinant representation, which then gives this object a rather decent mathematical definition. So that's the way, sort of, this is to indicate that, I mean, what I'm trying to indicate, but here I really don't want to go into too much details in order to save time for sort of, yeah, some aspects of the bigger picture which seem to be emerging. This is, in some sense, well, this works well for the class of cases we're considering here, but I do not expect this particular description to generalize very much further. I mean, it generalizes somewhat, but here you may. But in any case, what you see here is these guys basically, I mean, there's a way sort of to construct these guys out of the quantum curve. This is what I wanted to at least mention. And then there's basically a way sort of out of the quantum curve to define the tau function. The relation quantum curve to tau function is to a large extent pretty canonical. If you have, as we, and this was sort of the other bit of the coin, if you have a canonical way to fix here preferred systems of Darboux coordinates, these two ingredients are crucial. Quantum curve plus coordinates defining tau function. Good, but the main point, and this is what I really want to elaborate a little more on, is, well, if I say there's a line bundle, then how do I define it? Well, it's defined by certain transition functions. And the transition functions are difference generating functions, which are determined by the changes of coordinates from one chart to the other. This was the main claim. So very briefly, difference generating function is basically the same as, almost the same as a generating function, except that wherever you have in symplectic geometry, a relation by differentiation, you have a relation by finite shift. So you have a finite shift with respect to coordinate type coordinate gives the corresponding momentum exponentiated, and here for the other coordinate gives the corresponding momentum exponentiated. So this is closely related, but yes, something. Okay, so this is a difference generating function, and the claim is, okay, basically once you know the changes of coordinates, which in a typical example, namely the change of diagonal and triangulation, which is what in many cases the story boils down to, we're getting these rational transformations between different coordinates, which look like this. And yeah, then you can just compute the associated difference generating function by solving the difference equations, defining it, and you find something which you can express in terms of the Barnes G function. But what you can also find in this particular case is a nice expression in terms of Rogers dilogarithm, which will become relevant later. So these things are basically known objects. I'm calculating here a relatively simple example, but so there are more complicated examples, for example, describing the change of Pan's decomposition of the underlying Riemann surface. These will not be quite as simple. These will have somewhat more complicated expressions. The point, however, being they're all built from the same ingredients by some apparatus. And so basically here what we see, these function E and the Barnes G function, they appear as the basic building blocks for the definition of these difference generating functions describing the changes of coordinates from one system of Dabou coordinates to another. So this is so basically the changes of coordinates define associated difference generating functions, define transition functions of this line bundle. So what I'm trying to convey is that how natural sort of this description is based on really the underlying geometry, namely there is a basically canonical deformation of the underlying geometry, which was the torus fibration, which then produces these cluster-like transition functions between Dabou charts. And this now is used in order to define a line bundle over our space. And this is what is being claimed here is the geometrical basis for this characterization of the partition functions.
So just a question, in your cluster-like transformations, do we okay, my question is between your it's a silly question, but I don't remember the answer. Is it G string or G string squared that plays the role of H bar for this problem?
I think it is okay. Actually, yeah, this is something I should double check carefully. I believe it's G string.
G string. Okay.
There's probably a reason why you're asking, which probably has to do with the relation between closed and open and stuff, right? So well, both play a role. I think actually, if I'm thinking about it, here in this part of the story, it would be the square appearing. Good, I can.
Oh, so in 3, for example, the shift is n times, I think, G string, not G string squared. It's x minus n G string.
Okay, there is a place where I can probably check this, which I wanted to come to later.
It's been a while since I thought about it, so I don't quite remember.
Yeah. Good. In these shift relations, you want to see. Oh dear, I was thinking about it, but also right now I must admit that I forgot a little bit. Okay, yes, in these shift relations, of course, we should rescale here, and then it would be, yeah, here it would be h bar, G string. So really in the rescaled, if you want, for example, here to express it through the periods, that is canonical coordinates in the special geometry, then you could write it, say, in terms of a over h bar minus n. So it would be h bar rather than h bar squared appearing here. So these are that's the order of the shifts. All right, should I?
Thank you. Thank you. I was just muted. Thanks.
Yeah, I didn't. Okay, so where are we? Where are we now? Good. That was basically, I was through with that. And yes. Okay, so now these were the tau functions, and then the statement was that we extract the topological string partition functions by these magic type of expansions, and this is what I want to really say some more about. But before I do that, I mean, what was said was, or reminded in the first part was that there was a physical understanding of that proposed by Dijkgraaf, Hollands, Zulkowski, and Waffer, relating this to well, partition functions in dual frames. This is the so-called dual partition function or I-brain partition function, and this, well, topological string proper. So it expresses a duality relation in string theory. Okay, so this proposal that we have, it has a rather non-trivial check, which is for some cases like C04, we can check it against topological vertex results. But if you wonder sort of what all this business may be good for, so in particular what it gives is some prediction or at least implicit computation of the results for arbitrary Riemann surfaces with genus G and N punctures, because well, the whole story has a pretty straightforward, well, to some extent straightforward extension, and it basically defines these guys then in this way. And this is where, in general, we do not know how to calculate with a topological vertex. So in this sense, it gives some, in this sense, I'd claim it has some computational power, because yeah, it defines or characterizes the thing rather precisely. Okay, so what I want to stress and a little elaborate further is I find it sort of pretty nice that really what defines this thing is this geometry hidden in the description of a deformation of this twistor space Z in terms of these cluster type taboo coordinates, and then the line bundle defined with some difference generating functions describing the transitions. And this, as I had explained in the first part, is basically all determined by the spectrum of BPS-states of, well, either the corresponding gauge theory, which of course has in string theory description as, say, for example, the Fukaya category associated to, well, A-branes in the B model here, that is Lagrangians on the local Calabi-Yau that I had introduced. So yeah, this and other points indicate that there is a relation between this proposal to the geometry of the space of stability conditions, and Tom Bridgeland is running another program in understanding this geometry associating natural geometric structures to the space of stability conditions, identifying natural potential functions or functions associated to this geometry and so on. And yeah, I really hope that sort of in the end we will discover basically we're doing very similar things. I mean, that there is a definite relation, I think, is undeniable, but what is not yet so clear is whether our favorite ways of packaging it do completely coincide. So.
When you say it's determined by the spectrum of BPS-states, what does this mean?
What does it mean? Yes, it is simply, I was stressing that basically, well, the coordinates are sort of determining sort of everything. Now, the coordinates, and in particular, then of course the changes of coordinates. And here, recall simply the spectrum of BPS-states is the missing data, which apart from this simple cluster type form, determines the changes of coordinates. So this here is the description of the change of coordinates. This will determine then the corresponding difference generating function. So everything basically which is really needed to determine it is here, the Donaldson-Thomas invariant or BPS index determining these coordinate changes. And then, well, okay, of course, this framework of GMN, more precisely the conformal limit thereof, gives a very even computationally effective way of how to determine actually the coordinate which are associated to a given space and a given collection of these BPS indices, which then of course, yeah, I mean, are locally constant over the moduli space, but undergo wall crossing at certain loci and so on. So indeed, yeah, these are sort of the data which determine how the coordinates that we start from, these semi-flat coordinates, which are the coordinates for the torus fibration, get deformed by h bar into the Darboux coordinates for our complex twistor space. Yeah, was it?
So are you saying that that there is a procedure where we would start, well, say start with a spectrum of BPS states and recover the topological string partition function, or did you tell us this?
This is essentially, this is what I'm trying to say. Yeah. So I'm arguing that for this class of examples, there is a very precise procedure doing just that, where, however, we use a bit more, which is namely the description of these coordinates via quantum curves and their exact WKB. But in the end, really, well, a crucial piece of information in the determination is for sure the description of how, assuming we have determined the partition function somewhere, how we continue it all over the modular space. And this is, of course, done by these changes of coordinates and this transition function business. Then the question is if we can fix the answer, say, asymptotically in some part of moduli space. For this part, for this class of examples that we're studying, the concrete description in terms of quantum curves plays a role. Okay. So,
yeah, so this part of understanding how to fix it somewhere, are we able to answer that?
Yeah, okay, so let me indicate. So again, it's sort of putting together the pieces. So a first key idea is, of course, that in some part, like the parts where we have this factorization, it leads to factorization of our tau functions. And furthermore, then of course we need to unambiguously determine these pieces. And the point is, the crucial bit is then to determine these pieces, including normalizations. And the answer is going to be that, okay, here I'm, well, very sketchy, but say for each of the possible factorizations, we have one type of graph, and this type of graph unambiguously determines then the normalization of the pieces. And so in the end of the day, it is the exact WKB. The exact WKB for this part, I claim, determines these 3-point function factors, or DOZZ factors, or how you may want to call them, which you have to fix in order to determine unambiguously these guys. So in this factorization, with the help of this exact WKB for the quantum curves, you're fixing all the possible ambiguities and end up with a completely unambiguous determination of this thing, which then, with the help of this factorization here, or this expansion, determines the topological string partition functions.
So you have a means of okay, we'll chop up the Riemann surface into 3 puncture spheres.
Yes.
And are you saying that not every 3 puncture sphere is the same as every other one?
That is exactly right.
Okay. And
so the 3 punctured spheres come in different types. Which, well, so it depends on where you are in the base manifold, whether you have this graph or this graph or this graph, and you find different results for the partition functions, which differ by some factors, but these factors have a meaning. I mean, they can be, so for example, if we compare this to the topological string calculations, then we have a similar story there. Namely, we have, say, toric graphs related by flops. And there's a dictionary between the type of toric graph and the Fenchel-Nielsen graph here. And only if you respect this dictionary, you will find a match. Namely, only then you will find that, say, the 4D limit of topological vertex calculations gives what these prescription, this proposal, which assigns partition functions to choices of coordinates, which are in turn determined by these networks or Stokes graphs, only then it works out, right? So it is an important feature of the whole story that you have these, what you may call, following GMN, framed wall crossing. Namely, the preferred coordinates that you want to use in order to expand your partition functions in, they determine on the piece in the moduli space where you're sitting in. And this leads to a, well, framed wall crossing phenomenon, which indeed we have to take into account if we want to get a correct check or correct match with the topological vertex results, because what it then matches with is the different types of toric graphs that are related by flops.
Okay, so the answer for my 3 puncture sphere depends on G string and 3 partitions, I imagine, right? 3 fermions.
No. Sorry, you should not confuse the. So here, this is basically the glued vertex, right? What is called the T2 vertex. You would compose it out of 4 topological vertices where you have these pairs of legs running off to infinity, which is coming from. Do you know what I was trying to say? So the topological vertex. Okay, so you have. I mean, this is something that would be nice to discuss, because that, I think, is one of the next steps we should discuss. But I'm in 4D after taking the geometric engineering limit.
Yeah.
Ooh. And so what this produces is then, well, these say 2-sheeted coverings, where then the 2 sheets are in correspondence, say, with 2 of the 3 fermion legs that you have in your picture. So this thing would correspond to something that we glue together from. We take 2 parallel legs.
Are you saying that the downstairs curve, the downstairs curve is a sphere with 3 punctures? Is that what you're saying?
That's right. Yeah, that's a
okay, fine.
crisp way of saying it, exactly.
Okay. All right. Good. Okay. Good. Now I have right. And
so yeah, from the vertex, it would come by taking this thing which has 3 composed legs, which are like 2 parallel legs running off to infinity.
Yeah, I'm familiar with that. Yeah, and you're saying that there are different limits in the moduli space of the internal thing, of the upstairs curve, where these 3 these different pictures would become relevant for describing the downstairs story.
Yeah.
Okay.
Yeah.
And when I
mean, in these terms, these would correspond to chambers. I mean, on the A side, to chambers in the Kähler moduli space.
Right. Okay. And when we are But your free fermions, they live on the upstairs curve or the downstairs curve?
Well, on both. So the way to think about it is, I mean, here, what is most practical for us is actually to think about systems of fermions with non-abelian monodromy on the downstairs curve. But what abelianization, which is of course just another way of describing the story, would provide is an equivalent description in terms of a system of fermions with abelian monodromy on the upstairs curve. And that is really the thing. These should be the fermions that you had.
But basically, at every point of the downstairs curve, I have a pair of free fermions, right?
Exactly. Yeah.
Okay.
Corresponding to the two sheets of this
Yeah.
covering.
Yeah. Right. Okay.
Right. So.
Okay.
Yeah.
Okay.
Okay. So. Okay. Actually, you should tell me how I'm doing with the time. I'm afraid I'm not getting very far, but okay, let's see. So here we have this formula. Good. We're basically done with it. Yes, no, that's fine. So a kind of moral way of summarizing it is that the highest genus corrections of the topological string are encoded in canonical H-bar deformation of these moduli space of complex structures on the mirror y of x. And this is what I'm trying to, what I will be trying to elaborate on in some way. And well, but one thing I want to stress is that this way of describing it, I more and more believe, or that it has a good chance to generalize between this class of examples. So, because it uses features, it uses structures that exist in the problem in much larger generality. I briefly want to mention some relation to work of Piolin et al., who had set up a program to describe the geometry of hypermultiplet moduli spaces where very similar objects and structures appear. And then I want, and this was sort of meant then as a, well, invitation for discussions, discuss some relation to the quantization of moduli spaces of complex structures. So far, we have not really seen quantization of moduli spaces of complex structures yet, except perhaps for the notion of the quantum curve itself. But the moduli space itself, in some sense, remained classical, right? Because we were we were using classical coordinates, which did not generate a non-commutative algebra in the description. And how, I mean, basically what I want to argue is that this is just, this was just quantum theory in disguise, where the quantum bit perhaps is in these, like, that there's difference generating functions rather than ordinary generating functions. Okay, so perhaps about point A, a few remarks. So what were Alexandrov, Persson, and Piolin trying to do? They were in particular trying to describe, to cook up a way to describe NS5 brane corrections to the geometry of hypermultiplet moduli spaces. Well, first of all, the first bit is basically they were using very similar ingredients, namely they were using twistor space methods locally, some moduli space M, which in fact was in their story also intermediate Jacobian fibrations, and atlases of Dabou coordinates on that space. And then they were combining mirror symmetry, S-duality, and the twistor space geometry to make a prediction for the quantum correction from a single NS5 brane, but they also have some ideas about higher numbers of NS5 branes. But let's focus on the case of a single NS5 brane. Namely, they were arguing that the quantum correction for a single NS5 brane is basically fully encoded in some potential, namely locally defined holomorphic functions, which have a representation of a form that we've seen before. So I'm really trying to argue that this probably wants to be the same thing. Where here we have a function depending on the two types of, I mean, basically on coordinates and momenta having such a polarization in the system of Dabou coordinates. And then by doing essentially the Fourier expansion with respect to momenta, there's a function depending on coordinates only. And what they furthermore was arguing in their framework, in their story, was that using basically MNOP correspondence, or the relation between Donaldson-Thomas invariance, Gromov-Witten, that the thing which appears here in this expansion is actually the topological string partition function. And it's really now, I mean, then looking at this from our point of view, it seems we may basically just have rediscovered their proposal, but probably with some, well, added value or bonus features. I mean, we have, as to the best of my knowledge, there were very few examples where this proposal was worked out or even checked or verified.
So this is for sense, one NS fibrin wrapping the whole Calabi-Yau?
Yeah.
Well, this is, it's very likely this is dual to 1d6 spring wrapping a whole Calabi-Yau in some dual frame. I mean, this is almost.
Right. Yeah, that's probably what, yeah.
Yeah.
Okay. In any case, well, I would say that our story then gives a nice playground in which all this can be made much more precise and concrete, and where you have a nice supply of examples to play with to illustrate their story. And for us, I would say this relationship indicates that indeed these key features that we have are indeed pointing towards well, large class of generalizations, in particular the story that the basis of all are these taboo coordinates, the associated changes of coordinates, and then there is this well, the dual types of potentials, one living on the full moduli space, one basically living on the base manifold related by this peculiar transform. This well, was absolutely crucial for our story, and I mean, a lot of sort of the way it was coming about was simply by trying to understand what this means and what consequences the existence of such transformations has mathematically. And yeah, here it came back in their story. And now this is what I want to well, at least say a little bit about, namely this here I want to argue has a interpretation as a classical quantum relation. So here basically we see a classical moduli space by this transform related to a quantized moduli space, and this is really what happens to the topological string. So here's the wave function, right? So whereas here, okay, you in retrospect can also interpret as a wave function, but it was defined in basically completely classical terms in terms of geometry of this moduli space M. Good. Yeah, as a warm-up, just let me remind, but I don't really have to do this. Particularly, one of the main players here is Mina behind that, so that it was, of course, argued for a long time that homogeneous corrections can be described in terms of non-commutative deformations of the geometric structures which are relevant here, which are the base or possibly the intermediate Jacobian fibration. And yeah, what this basically, I mean, a key feature of all this is to interpret the topological string partition function as wave functions. And now I want to argue that this is when you sort of just translate our description from this side to this side via the relation, this is exactly what is gonna come out, namely a quantum theory interpretation of these guys. Here it is. So let's maybe just write it for a single modulus case where we just have a single parameter here, just to simplify notations. Now, of course, we can invert this relation to compute the Zi top by just taking, I mean, maybe just here the inverse Fourier transform with n equals to 0. So we just can compute this guy here, of course, once we know this guy. The interesting thing is to I mean, one of the most interesting things is to see what happens to these changes of coordinates, which we had described here in terms of difference generating functions. So they looked like this. So these were relations where we just have a multiplicative factor in the tau functions associated to different charts. Well, if you just plug this in here and do these transforms, I mean, that's just a few lines, you will find, of course, that these multiplicative relations turn into more complicated relations, namely actual integral transforms with the kernel. This kernel, of course, is determined by this factor here. So yeah, so already this looks pretty quantum, but for the moment, it's just a straightforward consequence of just the inversion of this magic transformation between this side and this side, which was expressing duality between iBrain picture and topological string picture. Okay, so this looks like quantum theory, and I want to claim this is quantum theory. And we know which one it is. Namely, it is a variant of quantum Teichmüller theory, which probably is even better understood as a variant of complex Chern-Simons theory. Concretely, here what it would amount to is, in purely algebraic terms, non-commutative deformation of our moduli space M, which here in fact has an incarnation or a description as the SL2 character variety. The moduli space of flat connections on the four-punctured sphere, which is described in terms of coordinate functions, which would be just holonomies around, well, a natural set of cycles. So here it's natural, say, to take the curves which are separating pairs of punctures from each other. Like, for example, one cycle is, we call it STU, following Mandelstam, and S would be separating punctures 1 and 2 from 3 and 4, and so on. And so their associated coordinate functions, the corresponding trace functions, the traces of holonomies, so which we call here theta. Theta S, theta T, theta U, and good. Classically, just by trace relations, it's a classical story that they satisfy some relations, and these here, okay, I already wrote quantum relations, so the definition of the quantized algebra of functions on this moduli space by generators and relations, where here the first three would in the classical limit turn into Poisson bracket relations, and then there's one relation for which is really describing the cubic surface that this moduli space is as an algebraic variety. Anyway, this is something.
So people have written this down in some context, is this Q deformation of the character variety?
The Q deformation of the character variety was written down in some contexts. I think for this case, these formulae, I should double check, but I think they first appeared for this case in our paper with Grisha Vatanov on the quantum Teichmüller Liouville AGT story, where of course, yeah, it plays a role, but here it plays a different role. I mean, it's not unrelated, but of course the type of interpretation is quite a different one. And we are actually in a different regime, which is quite important. It's not exactly the same story. So this is why I wrote here variant. The usual quantum Teichmüller theory would correspond to this, what you call refined topological string, then the real Nekrasov parameters, which correspond to a squashed four-sphere partition function, and then the topological string corresponds to this unrefined case, which is not unrelated, but there is a subtlety to get one from the other simply by analytic continuation. This does not quite work. So anyway, this is more like, but I mean, on the algebraic level, this is the same thing. Differences concern the representation and then the exact special functions that you have to use in order to build all these integral kernels. But that's a little more like technical points. Okay, so we have this character variety. We have quantum generators and relation description. It has appeared in the context of quantum Teichmüller theory, which has a relation to complex Chern-Simons theory, which is understood to some extent. I wouldn't say completely, but to some extent. And yeah, so then you can play here the game with Forgontroff, quantize them, or Fenchel-Nielsen, quantize them. These give different charts with Dabou coordinates, which have quantizations, and all these are related by quantum cluster transformations. And yeah, if we simply, so these quantum cluster transformations would simply be the integral transformations that we have found. Just note, these are sort of two things coming from two sides, right? You could start just classically, work out here these difference generating functions. This defines the integral transformations. What I'm saying is the guys that we define in this way happen, well, for a reason to coincide with something that basically you can define from a completely different view in somewhat different terms by simply playing the game of quantizing this character variety, quantizing the Dabou charts, and then constructing the quantum cluster transformations. And the relation between these two is here this magic relation. So this is where the two things meet. Then
can you explain this a bit more, or like what it is?
Good. So
how do I translate these relations into the ones you had on the previous page?
Okay, so yeah, so you can either start by constructing these guys, invert this relation, thereby construct these kernels. That is, say, method number one to get integral transformations, which from this point of view are not yet, where it's not yet obvious sort of which quantum theory they describe, right? So we need to.
But these integral transforms require very little. I mean, it's basically say as little as a Fourier transform, or if you want, you know, if you don't want to change x and p, you want to change that. You know.
The non-trivial thing is of course here, right? So then of course to translate it into these transforms is basically trivial. I agree.
Right. I imagine that you can get a story which is completely consistent here. Yes.
Yeah.
What does this have to do with your with the second page?
Now the second page is I'm saying you could play the game as was played in the context of quantum Teichmüller theory or complex Chern-Simons to quantize the character variety. Then what you would do is to simply introduce, for example, Forgontroff coordinates. You quantize the Forgontroff coordinates. You quantize the flip. It is represented in terms of quantum cluster coordinates as integral transformation of this type. Claim, theorem, these are going to be the same. So what I do thereby is to identify basically which quantum theory we're talking about, which quantum theory we have sort of implicitly defined by doing the game of inverting this transformation. Okay, so here came a quantum theory through the back door by just inverting this transformation and then translating these transformations into something which looks like quantum relations. Now, I'm just by matching these guys with something known, namely with what is coming from quantum Teichmüller theory, I'm identifying what kind of quantum theory we're actually talking about. Namely, it's the quantum Teichmüller theory, the quantization of the character variety. As of course you might expect, but simply here is sort of the proof, if you like, the proof would be by matching these kernels to what you would construct by doing the game of quantizing this guy here. In particular, what we have identified thereby are sort of natural quantum observables to study. Right, so these were, of course, you could also here, I mean, you can just multiply these guys with trace functions, and then you can invert the transformation. Okay, so then what would that be? That would then be difference operators acting here, which then gives non-commutative, in general, deformation of the algebra of trace functions. Well, yes,
I'm not completely following. I mean,
okay.
The previous page basically comes about as saying, okay, the A and the B periods are like, the x and the p coordinates of some phase space, and magically the topological string partition function transforms really exactly like a wave function. So this case is a as simple guy as you can possibly imagine. Okay, so and so what you're saying maybe is that on the other side you sort of get something analogous, so that like the s and the t period, I can think of them as like e to the x and e to the p, and then the u period is e to the x plus p, and that's basically all that's behind this relationship. Is that what you're saying?
In some sense, yes, although there is what is coming in addition is the deformation of A and B period into the Dabou coordinates of either Fock-Gonchoroff and Fenchel-Nielsen type, right? So they coincide with the A and B periods only to leading order in the H-bar expansion. So the point is really that yes, you have a deformation here of two types. So on this side of the story, in the I-brain picture, you have what you could call quantum periods, right? Which are, however, classical objects generating a commutative algebra, which, however, are H-bar deformation of the period A and B. So these are the H-bar deformation of the periods A and B by a lot of H-bar correction into some commutative objects, which you could call quantum periods in a way, but in some sense quantum is a misnomer there, because it's coordinate functions for a classical moduli space. So you're basically just H-bar deforming the complex structure that is parametrized by A and B periods into one which has these Fock-Gonchoroff or Fenchel-Nielsen coordinates as the holomorphic coordinates functions defining the deformed complex structure. So this is sort of the geometric side in the I-brain picture. On that side, it all becomes non-commutative. So then here you're having basically non-commutative deformations of A and B periods, which represent quantizations of, say, Fock-Gonchoroff and Fenchel-Nielsen coordinates. That is sort of the emerging picture. Yeah. Okay, so yeah.
Just to ask you one more question.
Yes, sure.
Supposing in your formula here, in formula 8, so I know that I have to be careful what I mean by x, and so I usually suppose by x I just meant the ordinary classical A period, and by x hat I meant the ordinary classical B period with no H-bar deformation. How much mistake would I make? What would go wrong? Which part of the story breaks? What forces me to use some H-bar deformed periods?
It would simply then it would simply not give you the right partition function as via this machinery. I mean, it would give you another. It would give you another function. So
in the topological string partition function, it is a function of the ordinary A period. I mean, the x is just they're just the A period. That's what we mean by topological string partition function.
Yes, right.
So x and x. Okay, maybe I'm not understanding anything. I think I think that's what's going on.
I mean, right. Okay. It is kind of tricky. Here is something that might help, although it also will take a moment to digest. So no, it does not. Probably it does not help. I'm not sure. Okay, let's maybe.
Okay, we can keep going. Maybe I'll. You're claiming that you have a new way of calculating topological string partition functions.
Non-perturbatively, and some yes, with a high potential for sort of a more general picture.
So yes. You understand well now, how they transform if you go from one patch of the moduli space to another patch. And you say you also have a method of calculating in some specific patch by sewing.
That's right. That's right. So in specific patches, there's a very concrete way of, say, then generating series expansions in the sewing parameter and so on. So this is
and do you have
part
a
of
way
the
of calculating in a single patch, or you also have a new way of calculating in a single patch? Plus, of course, you have to know how to solve, but you have a new way of calculating it somewhere, like in one patch. Is that correct?
Yeah.
Okay. All right. Yeah, it's important. I mean, this is hard business. It's hard to somehow get it. Maybe. Okay.
Yeah, I'm understanding that it's a little like good. I'm trying sort of to also I'm focusing on a certain aspect which I think is the most important, which is the importance of these natural geometric structures, which seem to be basically underlying the whole story, right? In many different incarnations of the topological string, be it BPS counting, be it Gromov-Witten, and so on, it seems that ultimately there is these geometric structures of the moduli spaces underlying it, which have these two phases, being the moduli spaces of complex structures, but on the other hand, they have this other phase of being spaces of stability structures, right? But all this, I mean, I think the magic is, and this is what sort of mathematically explains various duality relations on that level. The magic is that the geometric structures that these spaces have, are the same. For good reasons, of course, and for string theory, it's not at all surprising that, I mean, it comes from the worldsheet description of branes that the moduli space of complex structures is the same as a space of stability conditions. But this seems to be really, I think, a central, say, collection of structures for the mathematical understanding of what these things really are. Anyway, here I just wanted to sum up what I had previously tried to argue, namely that this transformation here brings us from a basically classical picture to a quantum picture. And in fact, this was already in the derivation of this tau function conformal block relation of Lissovy et al. That we together had given, namely where we had observed that this transformation basically diagonalizes the action of the Verlinde operators here on the conformal blocks into something classical on this side. This was the key idea in our paper, and here it just gets reinterpreted in terms of topological string context. Okay, so here's a little bit of like message, but I said it probably already. So what was encoded in a H-bar deformation of the geometry sort of on the I-brane side gets translated into a quantum deformation of the moduli space really on the topological string side. And these changes of patch now, well, I mean, the tau function being a line bundle gets translated into this being a section of some infinite dimensional vector bundle over the moduli space, describing the quantum version of the transition between charts. I had mentioned last time briefly, but I don't really have so much to say about it. It seems maybe from some points of view, math is getting at similar, probably closely related things, namely some work of Bousseau very recently has within the context of basically a quantum version of Gross-Seibert program found the quantum cubic as the description of, say, higher genus Gromov-Witten descriptions, Gromov-Witten invariants for the mirror of the cubic surface, which, the cubic surface, when you simply work out the relations, would be what corresponds to the Hitchin moduli space for 4 punctured spheres. So the circle kind of wants to close here. That's a side remark. Well, okay, let me leave it with this. And maybe make one
Not
more
quite.
remark.
His cubic surface comes from local P2, and I think your comes from local P1.
No. He has different stories. He had in 2019 a series of papers on local P2, which I also started looking into because I would like to, of course, do a similar story for such Calabi-Yaos as well, and I see a very good chance for doing this. But this is,
I mean, anyhow, I think you can do basically anything whose mirror is a local, is a genus 1 curve, and so all of these are in that family. So.
Yeah, but I mean, okay, what one has to be careful about is there is. Here we're talking about sort of the mirrors. I mean, this here is the mirror symmetry. So what he was talking about is the mirror symmetry on the level of the moduli spaces. Right, so the moduli space, say of this M-Hitchin moduli space C04, well, concretely it is related to the cubic surface. It has a mirror. And this is also computed by, say, Gross-Siebert and so on. Then Bousseau's story is to add the homogeneous corrections. And then they have these beautiful, but for me still mysterious canonical coordinates on the moduli space, these given by the so-called Theta-functions. And he ends up giving a generators and relations description for this. So this is basically what, in terms really of generators and relations, defines the the mirror classically, and then adding hygienous Gromov-Wittins, it gives a non-commutative deformation. That is Bousseau's story. And he computes it for this example and finds this. So this is his main result, basically, in this paper for cubic surface deformed by higher genus Gromov-Wittins. And well, this is no accident, but I do not claim that I fully understand all this. In fact, I find it extremely intriguing, and I would really like to make it a kind of big unified picture where this is just one and the same story ultimately. So good. I don't know how I actually don't have any like control over time anymore. So if you can give me some indication where I stand and how long you want me to go on and ramble here.
Well, as long as you have things to tell us.
Okay, good. I can go on a little bit, at least this year I would really like to tell. And this year maybe, yeah, okay, maybe 2 more slides if you like. And then, so this one is perhaps, well, what have people also done? There was the idea that the wave function description of the topological string should come from the quantization of H3, or maybe the lattice in it, which is the intermediate Jacobian. Okay, what is of course well known is for these local Calabi-Yaos that H3 for these local Calabi-Yaos becomes essentially the H1 of this curve sigma we're talking about. So how about, I mean, does our story have a relation to geometric quantization of, say, the torus fibers in our torus fibration? And it seems yes. So here is a basically mathematical theorem that we can prove. So what we're combining here, and this I think has a relation to also this point that you, Mina, found confusing. What we're doing here really to define, what we're doing here is to define a theta function, which is a function really of period variable, and then coordinate on the torus fiber by taking the tau function, which was a function of, say, Venturi-Nielsen or Fock-Goncharov type coordinates, which themselves via holonomy map are functions of period the torus coordinate and h bar. So this is, if you wish, yeah, the quantum period defined by holonomy map. So it's the composition of, yeah, tau being a function of like Venturi-Nielsen-Fock-Gonchov, and then we are composing it with holonomy in order to define what I call the theta function, which is really then function on the torus fibration and h bar. Z is just the complex structure of underlying the downstairs curve, the underlying curve. So this is what we have in a say one parameter example.
What's theta?
Theta is so we have this torus fibration, the say Jacobian of the curve. So then that's the flat coordinate for the Jacobian of the curve. Okay, so here's just sort of the relation to the previous notations, but never mind. So I think this is probably hopefully clear enough. So now here's the claim. We can now just ask ourselves what happens when we send h bar to 0. What is this beast that we've constructed becoming then? Well, we have to regularize. So the leading bit is actually given by is the same. So the leading divergence in h bar, there's a singular behavior of the logs, which is just the same as the one of the topological string partition function, which we of course all know to be given by the prepotential. So here's basically the prepotential coming as the leading bit in h bar to 0. The interesting bit is, yeah, what's in here, right? So what does this give basically to next to leading order? And here's the claim. It's the theta function on the torus fibration, right? So this is how I would define it just classically. So here the tau is the one given by the prepotential. And then this is just the standard formula. In other words, this here, our theta function, which is essentially, well, composition of tau function with holonomy, is a basically canonical h bar deformation of the theta function on the Jacobian torus fibration. And this in turn, I mean, if you just think about geometric quantization of this Jacobian torus fibration by just, well, the classical arguments of how you would geometrically quantize a torus and so on, it would give, I mean, the geometric quantization of the torus gives the theta function. So this is some pretty well-known fact. And in this context, if we have the torus fibration, and if we have, for example, I mean, what this h bar deformation does essentially is in particular to smoothen out what happens at singular fibers and so on. So it makes it all very nice and defines an h bar deformation of all that. But to leading order, the thing is nothing but a theta function.
And theta and eta, are they the same thing?
Theta and eta, so
how is the theta related to the old eta? Is it
okay, eta.
So you have eta in the
so eta was okay. So so we had sigma and tau. Sometimes this tau I was calling eta, unfortunately. So that is in any case this conjugate coordinate to, so it's basically related to A and B cycle period, but then here deformed into quantum period. Okay. Okay. So this is sigma and tau, which is becoming, I mean, here's a, okay, let me recall perhaps one thing that is also pretty important for this relationship. Namely, here is the semi-classical, the h bar to 0 behavior of these x and x check, which in the example become sigma and tau. Yeah, so this is sigma, this is tau. To leading order, we're getting the periods.
Oh, and there's the theta. Is that the theta?
And the theta,
Okay.
this theta here is basically, and here is the precise relation, the coordinates on the torus fiber. The thing that, yeah, really is sitting here over, well, the coordinates here for this guy, right? So the coordinates on. All right, so, I mean, it's really, it is the coordinate which is on the one hand expressing the linear structure of the torus, but which on the other hand, that is this theta, the coordinate, which is on the other hand expressing the complex structure of the torus. All right, so this is an observation. This is a result which I think still wants to be understood further and deeper. To me, sort of, I take it as an indication that this might be a nice illustration or nice class of examples where one can make these ideas of quantizing H3 and using it to characterize topological string partition functions more precise. All kinds of things sort of course, now should be asked, holomorphic anomaly, and so on. I don't know. It's a purely holomorphic story, all this. So
I mean, a holomorphic anomaly is just a statement that there's some other polarization which does not require you to choose A versus the B cycles. So hence, but basically, the reason you need to have different functions, right, in different chambers in moduli space is that the A and the B cycles themselves are not well defined.
No, I mean, okay, I understand this. So we have enforced holomorphicity by taking a holomorphic limit at the expense of, say, sacrificing globally well-defined objects. So we have, therefore, this is what leads to all this business of being just locally defined and having to change coordinates from patch to patch and all this. So in a sense, there must be a way sort of to trade all this business of coordinate changes from patch to patch for a globally well-defined but non-holomorphic description. But I think this would be...
To me, the most convincing part of the story is if you have a new way of calculating these topological string partition functions. Because the rest are interpretations, and we can, ask how clean they are, how powerful they are, but a real statement of power is if you can actually do a new calculation. And that's, if that's true, if this way of thinking about it gives you a new way of calculating things done, and that's really interesting, I think.
Well, I mean, okay, it calculates the topological string partition functions for a whole class of cases where they haven't been calculated before, which is all these class sigma cases where we have, for example, higher genus downstairs curves and so on.
Yeah. So if this line gives you that's an extremely strong indication that that's something is real. That's really interesting. Right?
No, I mean, I would, from this point of view, I would think it also has practical, like, computational power. Although, indeed, here in this talk, my attitude was more about sort of the conceptual hints as to the big picture in which all this.
Let me say differently. I'm not that interested in the answer of the calculation, other than its existence, right?
Okay.
You see, it's oftentimes, right, we don't actually care about any of these numbers, but the question of whether there's a deep new story or not is an existence of a new calculation. Right. Even though I'm not actually interested in like whichever genus, whatever thing, right? But if you have a new calculation, then the whole story around it is really interesting. Right?
Yeah, no, I mean, basically for a class of examples where it hasn't been calculated yet, it gives a very precise means of calculating.
So what's the limitation? What's the limitation of your new means of calculating?
Okay, actually, I mean, at the moment, it's just a class of examples where it's worked out, which is already bigger than what was known before. I would think it should have many generalizations. So, for example, higher rank class sigma cases corresponding to, say, the higher rank class S theories will be very interesting to look at.
So do you have an in principle an algorithm for that?
Well, the algorithm, you see, would then require us, I mean, there are some things which require serious work, but basically what this tells us is what to do. Namely, for example, for the higher rank cases, it would put the focus on determining coordinate systems of, say, Ventral-Usen type for like 3-punctured sphere, for which some first results are available, but okay, there is technical work to be done to really do the calculation. It's not completely trivial, but basically here, for these cases, for example, what this framework suggests is a very clear way where to go, how to go, what to do. Okay, perhaps one last thing, but just if you like to hear it, would be, well, so far it was all about basically the closed string partition functions. At least some open guys also have a nice interpretation in this story, which I think has some potential for being developed and maybe also leading to extra computational power ultimately. So we had this relation here between tau functions, partition functions. Now we can introduce branes, the ones invented by Mina in the toric case, but of course they descend. I mean, they have a clear relations to our fermions, corresponding also to say to surface defects in the 4-dimensional corresponding field theories. And yeah, so one can then consider expectation values of these guys at maybe 2 different points of the curve. And well, already sort of in the work with Lissovi, we had actually a generalization of this story to expectation values of this type. So what they do is to, what do? They relate fermions, say on this side, the I-brane side, to degenerate fields on this side. So basically in the non-commutative world, the fermions become the degenerate fields. One of the things, well, probably, I mean, I would love to discuss maybe with you at some point if you're interested. I mean, I started thinking a little bit about then really toric cases, that is going back 4D up to 5D. I think there should be a beautiful story sort of reinterpreting what you did with digraph and so on in terms of all this business of coordinate changes. I mean, you had a business of coordinate changes basically to calculate the topological vertex, right? And I think it is a natural generalization of the story that we discussed here, where one, instead of say the 4D framed wall crossing, one then has add surface defects in order to get some additional sector, and then gets a problem of 2D, 4D wall crossing and all this. Which is kind of, I think, useful in the sense that we had, as part of the formalism to compute these tau functions, we were using some, well, in some sense, relatively standard relationship between this thing here, which is related to the solution to the differential equation that we call the quantum curve. So that is the solution to the differential equation defined by the quantum curve here. And to go basically from the psi to the tau, right? Because in some sense you have to, it suffices basically to factorize this thing here in order to determine here these building blocks in the factorization. And these building blocks basically are from the simpler Riemann-Hilbert problems corresponding to a factorization of the quantum curve in like that. And that sort of determines then here these pieces, and well, the rest is just free fermion factorization of a conformal block. In other words, what I'm trying to say is that basically there is a pretty canonical way to go from the psi up to the tau, which is basically free fermion business. Therefore, being able to determine this thing here is in some sense sort of, so probing the story by the fermions, there is a, well, there's a formalism which basically reconstructs this guy here.
Yeah, so this is, I mean, if it should be true that if you know the top, you know the bottom, and vice versa. In fact, if you, essentially the tau function should be just some giant determinant, right, of free fermion correlators. Right? This is
right. That's what it is exactly.
Yeah, this is some kind of a, I guess, open close string.
Yeah, I mean here the new, right, so the new thing is here to add some open string sector that is represented by these psi's, and well, the nice thing is that somehow, well, you can view it as probes or of observables, and being able to characterize those. So these are sort of very direct. I mean, the nice thing is these are pretty directly characterized by the quantum curve, right? Because this is just a solution to the equation by the quantum curve. There are also then some normalization issues here, which are pretty important, because the normalization of this guy basically induces the normalization of this guy. So, but in the end of the day, the moral of the story is that yeah, there's a very close relation, and essentially one determines the other, and so therefore it may be convenient to sort of implicitly characterize the thing one is after through this object here as a probe. And something of this type is already sort of manifested in our formalism, and yeah, and I think it would be interesting to develop this further and in other examples and so on.
Okay. Okay. Joerg, thank you. Let's see if somebody else has more questions. Okay. Yeah, this is it's a striking story, and it's striking how many ingredients come together in it. And I think you're right that we're probably this.
Yeah, I mean, as I said, so indeed it's kind of amusing. I mean, for a long time I was, I guess, also most interested in whatever gives a new method to calculate something. Here at the which this does, I believe, and in particular going to these higher rank cases, and maybe, for example, these T3, these non-Lagrangian cases, where I think a lot of mystery is still there, is very interesting. At the moment, sort of what I think fascinates me the most is that there seems to be all these relations to mirror symmetry and the precise mathematical way of actually describing it and so on. So that there is there's these kind of universal geometrical structures behind of these moduli spaces, which have to do with mirror symmetry a lot, which basically seem to rule everything. And this is, for me, what I really like to develop more.
So actually, Bousseau gave us a talk, not last week, but the week before, right? Where he reminded us that there is a canonical relation between an open string and a closed string, which was so in the flavor that he told it was originally set up by Jacobian and Waffa, actually as means of explaining Kontsevich-Sobelman formula, and where I mean he and in fact that story to some extent works Well, it should work naturally, in fact, for the defined topological string as well. But anyhow, it's a place where directly the parameters your topological string depends on, especially the one with you know, I mean this tau function, exactly come from they basically parameterize disks in the open string. So that's precisely the setting that one needs, I think, for this relation, you know, relation to this gross conservative story, and also the cluster transformations, the way they enter. So I think that's what the story is somehow wants to be about, and it's quite striking.
Exactly. Yeah, this is, I mean, right. I had been looking into his papers. I do not claim to understand everything, but these points I also saw there, and I find them extremely striking, in particular in the relation to all this story. Furthermore, you mentioned Chicotti-Vafa, right? So,
right.
In particular, what they had is, well, they had the relation via sort of this Witten's open topological string story to abelian Chern-Simons.
Yes.
Right,
yes.
Where it's basically then the Chern-Simons, the abelian groups correspond sort of to the directions of the torus fibers. They would be here sigma. This in turn, I think, is related via abelianization of Andy et al. To the non-abelian Chern-Simons, which here appeared quantized, right? So I think, I mean, this is indeed sort of, there are all these ingredients I think want to combine naturally here. The relation, to the limited extent I understand it, of that Bousseau, for example, for the P2 cases had stressed a lot. So he was there, I think, considering on the one hand, so he was considering, I think, two a priori different but ultimately related problems, namely BPS counting for the local P2 on the one hand, and then I think the mirror symmetry for the moduli of the local P2 on the other hand, as computed according to Gross-Seibert. And the point is that there is this relation between, I think, the holomorphic disks that sort of give these corrections in the Gross-Seibert program. They are, because we're talking about hyperkähler spaces, related to Lagrangians by some hyperkähler rotation. This is what he, in his papers on this local P2 thing, presents as basically a heuristic explanation for the relation that he then in a different mathematical way actually proves in his papers.
Right. Yeah. So that's right. That's how Chicotti and Vafa set it up. So they wanted to compute on one hand some partition function that counts closed BPS-states, and they rephrased it as a calculation counting disks, ending on a D brane that wraps the S curve, which is or the mirror curve. So yeah.
And I believe this is also sort of, I mean, these are just sort of different incarnations, different examples for this general pattern, right? Because here, basically what was controlling all these quantum corrections were the spectrum of BPS-states on the local Calabi-Yau. But then it ended up controlling the quantum corrections to the moduli space, which appear in mirror symmetry and then get quantized in the quantum mirror symmetry.
Right.
So it follows the same pattern.
The only thing is that in his story, in the end, when he gets the open string calculation together with its h-bar parameter, the answer, the question this answers is not the original topological string, but the topological string in the NS limit, which is
This was, however, yeah, I think this was sort of, this is a twist that was in one of the last papers. The relation, I mean, there is a kind of duality relation which I do not understand perfectly yet between the unrefined and the NS limit. In some sense, what I do understand pretty well for this class of examples is that they certainly capture the same information in a way. I don't quite understand why or how exactly they're dual. I mean, well, there are ways sort of to prove they're dual by in some mathematical ways, but I don't really find I understand it conceptually enough. But I mean, they do understand. I mean, say mathematically. Well, the way sort of I would describe it is simply both basically boil down to the classical geometry of the modular flat connections. And that's where, I mean, all the information is in there, and they sort of package this information in different ways.
Right. It's interesting that the subject it still has apparently lots of room to grow after all these years. So that's fantastic. It's really nice to see. So, okay, Joerg, thank you very much for joining us again and for telling us about this. Yeah, so hopefully we'll continue this conversation.
Yeah. Okay. Okay. Thanks for the invitation. In fact, I felt tempted sort of to ask for maybe discussions, because there are some points where actually maybe well, it might make sense simply to discuss or join.
I think so.
So maybe we can sort of try to find some time.
Yeah, right. I think that will be a good thing. Yeah, this it's clearly a very interesting story. So.
Okay. So let's.
Okay. Thank you all.
Okay. Thanks.
Thanks for joining us. Okay.
Bye-bye.
Bye-bye. Bye, everyone.
Bye.